Today we're talking about molecular orbital theory, and this one is a little bit more confusing, and you will go into way more depth if you take inorganic chemistry. But I'm just going to kind of introduce it to you, and it kind of explains some of the shortcomings, again, of the other theories, which is why we also have this theory. So the shortcomings of Lewis structures and valence bond theory are that they don't predict some of the important properties that we see in molecules. We can get valence bond theory and Vesper structures to predict polarity. We can get hybridization to predict bond angles and explain those bond angles. But there's things like paramagnetism and diamagnetism that I'm going to talk about in a second that aren't explained by these other bonding theories, things that we observe that we need some other way to explain them. So first of all, what are these? Paramagnetism is when molecules with one or more unpaired electrons, so that would mean they have a orbital that only has one electron in it. And if you have those, they tend to attract to magnetic fields. So they're kind of like magnetic, right? So my question to pose to you is that the Lewis structure paired electrons, then why is O2 paramagnetic? So like if we are using valence bond theory to explain this molecule here, okay, O2, right? It has a double bond, so a sigma and a pi, and it's got these electrons out here. This is what an oxygen molecule, or sorry, an oxygen atom's electron configuration looks like. These two do an overlap for that double bond, so we wouldn't have any unpaired electrons. Everything would be filled. So why is O2 paramagnetic? We have to have some other reason to explain that because there are no unpaired electrons here. So why does it show a paramagnetic property? So paramagnetic is when you have unpaired electrons that will attract to a magnetic field, and diamagnetism is when your molecule has fully paired electrons and they tend to repel magnetic fields. So all of your molecules are going to be paramagnetic or diamagnetic, some more strongly than others. But then, for example, so N2 looks like this. N2 would have, this is its atomic electron configuration. All of these overlap for you to get your triple bond. And we have no unpaired electrons, and this one is diamagnetic. So this one is explained using valence bond theory, but oxygen is not. So we have another theory. Again, a theory is something backed by a lot of evidence that explains why O2 and a lot of other molecules show paramagnetism. Okay, so MO theory is, this is the general definition, is that atomic orbitals combine. So when I'm making a molecule, I have the atomic orbitals from one atom, so oxygen, for example, and the atomic orbitals from another atom, and they combine to form completely new orbitals for the whole molecule. We call those molecular orbitals. That's why it's called MO theory, or molecular orbital theory. So instead of being like a 2p and a 2p overlapping, we're actually going to combine those orbitals and they're going to make a new orbital. Okay, so similar to atomic and those hybrid orbitals that we've been talking about, these orbitals do have specific shapes. They have specific energies. They only hold 2 electrons. They still follow the Pauli exclusion principle, the 1 up, 1 down spin. And the number of molecular orbitals that you get when you combine them is exactly equal to and the same as the number of orbitals that you are combining, just like hybridization, right? I put an S and a P together and I got 2 SPs. So you're not making more orbitals, you're just making them into more different new orbitals. Okay, so we're going to use H2 because of these simplest homonuclear, meaning same nuclei, same atoms, diatomic, 2 of them, molecule. Okay, so if we're using valence bond theory to describe H2, we would say that H2 forms because of the overlap of those 1s orbitals. And we actually talked about this molecule when we were just introducing valence bond theory. In MO theory, we said that H2 forms when those 1s orbitals combined to make new molecular orbitals. So H2 has these new orbitals, and the molecular orbitals result from what are called constructive and destructive combinations. So when they combine, we get a constructive orbital and a destructive orbital. And I'm going to get more into those here. Okay, those are our new orbitals. Okay, so difference between a constructive orbital and a destructive orbital. So when I have my 1s for hydrogen and my 1s for the other hydrogen, when those orbitals combine, I get one that is constructive, which is like a positive thing, a good thing. It's constructive, right? Orbital that looks like this. And then I get a destructive orbital that they're really not combined that looks like this, okay? So the constructive combination is a new molecular orbital that increases the electron density between the nuclei. So the electrons would be able to overlap and interact and bond, really, between the nuclei. A destructive combination is a new molecular orbital that actually pull apart the nuclei. So this would be like not bonding, they're not interacting. So you get one that is constructive, and this is called a bonding molecular orbital, and you get one that's destructive that they're not combining, which is called an anti-bonding molecular orbital. So anytime I have like a 1s and a 1s, when I combine them, I get two new orbitals. One is bonding and one is anti-bonding. So I still have two orbitals. Those are the new orbitals. Okay, so those molecular orbitals that lie along the internuclear axis, that means between the nuclei, like this, think this picture up here between the nuclei, is a sigma bond. Okay, and that's kind of what we talked about before, right? You're bonding, they overlap. If they're going this way, right, together, it's a sigma bond. If they're above and below that, it's a pi bond. Same principle applies here. So when we combine a 1s and a 1s, we get a bonding 1s and an anti-bonding 1s. Both of them are sigma because these are both along the internuclear axis. Okay, so this is how we represent it. We say sigma 1s for the bonding molecular orbital from the combination of a 1s and a 1s, and sigma star, notice the little star there, 1s is the anti-bonding molecular orbital from the combination of 1s and 1s. So my two new orbitals are these. This is how we denote them. Okay, so then I have this orbital. Instead of having a 1s and a 1s, I have this orbital and I have this orbital. And those are options for my electrons to be in. They can either be in the bonding or they can be in the anti-bonding. So electrons that are in bonding molecular orbitals, as you can probably imagine, are good. That's a good thing. That means they bond. They stabilize the molecule. They are low energy, and low energy is good. That means it's stable. They're actually better than those original 1s orbitals. Whereas anti-bonding ones destabilize. They don't help with bonding. They are high energy. They're actually worse than the original 1s. This is sometimes how you will see these orbitals represented. Okay, this was my original 1s from this hydrogen atom. This is the original 1s from this hydrogen atom. And when we make our new orbitals, those are the ones shown in the middle. You get a bonding 1s orbital. So that's the sigma 1s that's down here. So you get one box down here. Remember, it's a lower energy. That's a good thing. It's more stable. And the anti-bonding one is at a higher energy. So you show them like this one, and then this one. And then just like our regular Aufbau principle, you start from the bottom and then fill. So both of our electrons, one from this hydrogen, one from this hydrogen, would go into this orbital, and they're both in the bonding orbital, which is a good thing. It's causing a good bond. Okay, so these are our new MO orbitals. Now you are not going to have to draw these orbitals. You're really just going to have to fill them in. I will give you what the new orbitals are. So this isn't going to be too difficult. So how does that get us to like, why do we have this, and talking about para and dimagnetism thing? Well, first thing I need to talk to you about is bond order. And we've actually introduced bond order before, right? If you have a single bond, we said that was a bond order of 1. A double bond was a bond order of 2, and a triple bond is a bond order of 3. The bond order, the more stable the bond, the stronger the bond, it's harder to break. The shorter the bond, they're closer together. So higher bond order is a better, stronger bond. Now, when we have MOs, or molecular orbitals, calculating the bond order is a little bit more difficult. We do have to actually calculate it. And the way that you do that is the number of electrons in a bonding orbital minus the number of electrons in antibonding orbitals divided by 2. And that's it. And again, the higher the bond order, the more stable, the shorter, the stronger bond. So higher bond orders are a good thing. Lower bond orders are not as stable, not as strong. Okay, so we're going to talk about some molecules that you might be like, I've never seen that before. That looks weird. For example, He2. Okay, helium doesn't like to bond. It's a noble gas, right? So He2, we would expect to not be a very good bond order. It's probably not going to bond very well. So if we do this molecular orbital thing, I start with 1 helium over here, 1s2, 1 helium over here, 1s2. These are my 2 new orbitals, just the same as my hydrogen ones were. But now I have 4 electrons to put in them. So I put 2 in the bonding and 2 in the antibonding orbitals. So to calculate my bond order, I go 2 minus 2 over 2, and that equals 0, which means that bond order is bad, right? It's a 0. It's not even a single bond. It doesn't bond, it's unstable. And this actually explains why helium-2 doesn't exist. That's not a molecule that works, because if I were to make it, the bond order is 0. Okay, so we're going to get into some p orbitals now. So what happens when we get past the 1s, right? We have those sigma molecular orbitals when they're end-to-end on the internuclear axis. And we've talked about pi bonding before. Pi bonding are above and below that bond or that internuclear axis. And that still holds true here. These are no different than the hybrid theory that we were talking about, the sigma and the pi bonds. These are just pictures representing the sigma like this, and the pi, the whole above and below thing like this. You don't have to be able to draw or anything like that, but it's just the same. Okay, so what happens when we get past 1s and we have some p orbitals? Well, this is what the new molecular orbitals look like. Okay, so we already did the sigma 1s and the sigma star 1s, or the bonding and the anti-bonding. Now then we would have, because 2s comes next, right? We would have a 2s bonding, a 2s anti-bonding. And then the p orbitals get a little wonky. We have a sigma here, and then we have a sigma pi, or sorry, a pi, 2 p's bonding, anti-bonding, and then another anti-bonding up here. You do not have to be able to draw these. I would give this to you, be like, these are the MOs, fill them in, and that's it. This is the structure of the molecular orbitals for molecules like O2, F2, and Ne2. Okay, and this is a different structure. They're actually in a different order over here for lithium-2, B2, C2, and N2, some of which you might recognize as common things we talk about, and some of them you might recognize as things that you've never seen, like Ne2, probably going to have a 0 bond order. But we can show that and we can explain it. So their molecular orbitals are difficult to predict. So that's why I will give you the new molecular orbitals and be like, okay, fill them in with the electrons and then calculate the bond order, something like that. Okay, so rules for filling MO diagrams are exactly the same as all of the other energy diagrams we've done. Fill the lower energy orbitals first. Each orbital holds 2 electrons with opposite spins, so 1 up, 1 down. Also use Hund's rule, the empty bus seat rule. So that means, like, if I'm up here in these pi orbitals, I put 1 in each before I pair them up. All the same rules. Okay, so an example I might give you is for O2. Oxygen has a total of 12 valence electrons, right? Oxygen has 6 valence electrons. So now I have 12. I'm going to fill in, this is my MO orbital. I would give you a picture like this, and you'd be like, okay, I'll put in 12, 2, 4, 6, 8, 10. And then these ones get spread out. Okay, there's 2 unpaired electrons here. Unpaired electrons mean that we can have something that is paramagnetic, and this explains the paramagnetism that we see in an oxygen molecule. Because of these new orbitals, we actually get unpaired electrons, which was not explained before. O2, we predicted with hybridization theory, didn't have unpaired electrons. But if we use MO theory to explain it, it does, and that's why we see the paramagnetism. Now, this picture over here, you don't have to worry about. This is just another way to represent it. These were the original orbitals. These are the new MO orbitals, but this is a little bit easier to see, which is why I circled this one. So again, these are the MO diagrams then for second period homonuclear diatomic molecules. These are just very common ones that we see and how you would fill them up. See, we still follow all of the rules. The littler ones have this order with the sigma, sigma, pi, pi, sigma, pi, pi, sigma. And over here, the order is different. Again, I will give you which structure you're going to use, and then you fill them in. Okay, so example number 10 says the superoxide ion O2 minus has been implicated in a number of degenerative conditions, including aging and Alzheimer's disease. Using MO theory, determine whether O2 minus is paramagnetic or diamagnetic, and then calculate its bond order. So we're doing O2 minus, so I would be like, okay, use this MO diagram. Okay, now O2 minus, oxygen has 6 valence electrons, so that's 12, and minus means I added an electron, so now I have 13. So if I were to draw the diagram, it would look like this, but I would have an extra electron in there. So that's what I've got down here, 2, 4, 6, 8, 10, and then I would go 11, 12, 13. So this does have 1 unpaired electron, and anytime you have an unpaired electron, we can be paramagnetic. Okay, so unpaired means paramagnetic. If they are all paired, like 2s, you get diamagnetic, so kind of think of it that way. So yes, it would be paramagnetic, and then I wanted you to calculate its bond order. Bond order is the number of bonding minus the number of anti-bonding. So the way to calculate that is you look at the structure and be like, okay, bonding ones are without the stars. So I would be like, I have 2, I have 4, I have 6, I have 8 bonding. And then the anti-bonding ones are the ones with the stars. So I have 2 here. And then I have 3 here. So that's 5. So it's 8 minus 5 over 2, which is 3/2 or 1.5. So the bond order for this molecule is 1.5. And that's it. That's all you would have to be able to do.